Okay. So here is the first problem. Okay, for a machine shaft shoulder shown below, small d is given, capital D is given, the bigger diameter, the fillet radius is given, R. The shaft is subject to a combined loading, a bending moment M, okay, and a steady torsional moment of T, which is shown here. The heat-treated shaft has an ultimate strength of 105 kpsi, yield strength of 82 kpsi. The reliability goal for the endurance limit is 0.99. So we need to find basically the factor of safety using all those 4 criteria, and of course the yield factor of safety. Okay, so a problem like this, where do you start? Well, let's do it the inverse way. Let's ask ourselves, what do we need in order to solve for the factor of safety? If you look at the formulas I wrote down earlier, pick up any of them. Okay, let's say this one. So it seems that you require SE, KF, MA, TA, KFS, KF, MM, and of course, in this case, D is given, right? So N is the unknown. So I really need to use this one, but it has the same ingredients. So let me try to write down what are the different things you need to solve the problem, and then we sort of will go in the reverse in figuring things out. So here's what we need to solve the problem. So we need the following quantities to solve for A through E. Okay. So first is, let me put the strength criterions which are given to us. SY is the yield strength, it's 82 kpsi. SUT is also given, it's 105 kpsi. We clearly need the endurance strength. Unfortunately, it's not given, I think. Let's see. Yeah, so we're given SUT and we're given SY. We're not given SE. So SE is an unknown, but we do know that you can solve this in terms of, let me put that in red. If you know the factors, Ka, Kb, Kc, Kd, Ke, I'm going to ignore F, it's the miscellaneous factor, Se prime. So we need to find all these clearly to solve for Se. Okay, then what else? Kf is needed, which is an unknown, but, and so on. So same for KFS. Okay, and if you recollect from chapter 6, we need Q and KT to solve for KFS. Q is the notch sensitivity, K is the stress concentration factor, KT comes from it comes from a table or a figure, which basically gives you the geometric parameters and tells you a value for KT, which you just read out. Q comes from the Newberg constant, square root A, square root R, if you recollect. Okay, so there are formulas for that. So KF, KFS is no big deal. Okay, then we have to decide the diameter. Now, one way of thinking is that there's a stress on the outer surface of the bigger diameter. There's going to be stress on the inner surface, and there's this thing which is the fillet. Clearly, the stress is going to be the maximum at the place where there's a fillet, but there's two options here. One is we could find the stress right here using the stress concentration, or we could find the stress right here where it's a smaller diameter, where the geometry just changes. Now, among the two, you want to choose the smaller diameter, and that's because the normal stress or even the shear stress due to m and t respectively are inversely proportional to the diameter. So we need to choose the smaller diameter, not the bigger one. So d is whatever was over here, it's 1.1. So sigma is proportional to d cubed, and tau is also proportional to d cubed. Hence, use smaller diameter. Yeah, I think I'm missing one more, well, few more things. I also need to write the moments, right? So I need TA, TM, MA, and MM. Okay, what are these? These are the alternating and the mean torques and moments. Okay, so if you look at this figure here, and the problem statement says that there's a steady torsional moment. Okay, so think of this torque, it's steady, it's constant. If it's constant, that has to be Tm. Okay, so in the absence of, there's no mention of an alternating one. So we'll assume that it's 0. Okay, then we have a bending moment M. Okay, so there's a bending moment, and then, we assume usually that this thing is rotating, right? Because there's a torque, it's spinning. And so if it's spinning and this M is constant, then the effect of the M is to provide an alternating moment M. So this M, even though it says, it just doesn't say anything about being alternating or constant, we know it is alternating because the effect of rotation makes the moment M become positive and negative. In other words, the top part is stressed in tension sometimes, in compression some other times. So MA or MM is 0, and MA is whatever is given here, 101,260. So let's put that down. So TA is 0, TM is 1100, inch, MA is what I just wrote down, 1 to 1260 lbf in, and then mm is 0. Okay, so what needs to be done now is we only need to find these things in order to actually compute those factors. So let's go ahead and try to solve for these factors. Let's start with, I think the easier one is KF, S, and KF. So what we'll do is we'll try to go to the appendix and find the figure which corresponds to such a geometry subject to moment M, and the same geometry subject to torque, and those both are available in the appendix. I'm just going to pull it from my saved files. Right, that's the one which has a torque. Okay. And that's the one which has the moment. Okay, our goal here is to only find out what the stress concentration factor KT is. Okay, so here, what we need to do now is figure out what these ratios are. So there is a capital D divided by D, and there's a R divided by D. So we know that R is, from the problem, it's 0.11, small d is 1.1, capital D is 1.65, which gives us R divided by D equals so that's 0.11 divided by 1.1, that is 0.1. And then capital D divided by small d is 1.65. 65 divided by 1.1, that comes out to be 1.5. Okay. Okay, so let's just roll our eyes and see where this is. This is probably not in the curve. So d, oh, it's 2. This is 2, and there's 1.33. So we don't really have 1.5 there. So it's somewhere in between those two lines. And then we need to go, so the top two lines, and then we need to zone on 0.1 for our divide. So that's here. So we need to go along this and somewhere in between. So that should be our KTS. Oh, it's not 1.5, I think, because let's see. So this is 1.6, right? Yeah. And the way I drew it, right. Something like this. It looks like it's slightly below 1.5, but not kind of. So I'll just stick to this is the problem from the book. I'll just stick to the value the book gave. But I would say anything in the range of 1.4 to 1.6 is perfectly acceptable in the exam. Okay, so I'll stick with KTS equals 1.42 from book. However, if you choose KTS anywhere between 1.4 and 1.6 is correct. Okay, we just use that. That's fine. Won't change the answer much. So let's stick to 1.42. Okay, so the next one is the one down here for KT. And so again, same thing. First, figure out what this curve we want. We want the curve which is 1.5. Luckily, that curve is available. It's this one. And then we need to get R divided by D of 0.1, which is here. This is nice, and it's right there. So we need to. Okay, now this is 1.6. It seems like it's 1.7, right? So 1.7 is what I would do, but the book says 1.68. So let's just stick with the book. But so KT is 1.68, says the book. But I would say KT in the range of, I don't know, 1.6 to 1.8 is correct. You can use either any value in that range. So we stick with this, and then we stick with 1.42 for this problem. Okay, so that gives us KT and KTS. We need to still find KFS and KF. And for that, we need to go back to our formula sheet and figure out. So we need to find the notch sensitivity, which is Q. And once we get Q, we get K. So there are different formulas for different types of loads. For torsion, the formula for the Newbert constant is 0.19 minus 2.5 10 raised to negative 3, and there's a SUT plus 1.35 10 raised to negative 6. Sorry, 10 raised to negative 5 SUT square plus, sorry, minus 2.67 10 raised to negative 8 SUT cube. So here SUT is 105 kpsi, and that's exactly what goes here. You don't need to convert anything because the units of A are in this units. Sorry, SUT is in that units. And so that comes out to be 0.0454. So once we get that, we can find the notch sensitivity. For torsion, it's given as QS, and the formula is 1 plus square root of A square root of R. So square root of A is 0.454, which we wrote there. The radius now is the radius of the fillet, and that is 0.11. And so the answer comes out to be 0.8795. And let's just round this to 0.88. So then if you want to find KFS, it's 1 plus QS KTS minus 1. So 1 plus QS is 0.88. KTS we found on the previous page, it's 1.42 minus 1. So that comes out to be 1.37, which is just saying that because of the notch of that fillet, the stress is actually going to be 1.37 higher than what it is without that notch. Just like the stress concentration, but for fatigue loads. Okay, so then we can do the same thing for bending. And I'll finish this. After this, I'll stop, okay? Because we're going to run out of time otherwise. So the formula for bending loads is 0.246 minus 3.08 10 raised to negative 3 SUT plus 1.51 10 raised to negative 5 SUT squared plus, sorry, minus 2.67 10 raised to negative 8 SUT cube. We put SUT equals 105 K PSI in this equation to get square root of A as 0.0582. And then the formula for, yeah, it is 8. You're also cubing, taking the cube of SUT, so it'll all work out. Okay, so that is 1 plus square root of A divided by square root of R, which is 1 plus 0.0582 divided by 0.11 equals 8508. You can just round it to 85. Okay, the last thing is Kf, which is 1 plus Q, Kt minus 1. Q is 0.85, which we just computed. And then Kt is from the previous page, it's 1.68. This one, so that comes out to be 1.58. Okay, so for all we need to find SC prime. Okay, so if you scroll back to the previous chapter, the non-adjusted endurance strength, or for the endurance strength for the lab specimen, is given by 0.5 SUT when SUT is less than 200 kpsi. So that fits. So there are two equations, I believe. One of the equations is less than 200, one is for greater than 200. So that's the one used for less than 200. And so then we sub in the value for SUT. SUT is 105. So we have 52.5 kpsi. Okay, so we've got SE prime. Let's compute Ka. So Ka is given by the formula A times SUT raised to B, where A and B are from a table in the book, and I won't hunt that down, but you can go back to the previous chapter and see it. So this is machined, as it is said in the question. So we need to go find the A and B for machined surfaces, and that is gives me A equals 2 and B equals minus 0.217. So 105 minus 0.217. So plugging in the numbers, we get 0.7285. Can be rounded to 0.73. Next is Kc. Sorry, Kb, my bad. Okay, Kb is the size factor, and that depends on the diameter of the shaft. So if you go back to the problem, we have two diameters here, capital D and small d, and the design is usually based on the small diameter because that's the one which has the highest stress, because stress is inversely proportional to d. So we use the smaller diameter, which happens to be small d, and it is 1.1 inch. So let's use that value. So this is from, again, from one of the formulas provided, 1.1 minus 0.107, which comes out to be 0.87. So this and this, C chapter 6. Okay, so that's KB. Now KC, that's kind of the interesting one because there's a KC given for bending, axial stresses, and torsion. So if you look at the formula, KC is 1 for bending. Okay, but if you see this particular problem, it's subject to two loads. There's a bending, and then there is a axial load, sorry, torsional load. So it's 0.59. So if there's such a case, what do you do? Well, it turns out that the lower the value of Kc, so Kc, by the way, can be, max can be 1. It can't be greater than 1, right? Because that will essentially mean that the endurance strength would, if you see the formula, it's Se is Ka, Kb, so on, Kc, Kd, Ke, Se prime. So as I said, Kc or all these factors can only be up to 1, can't be greater than 1. So the smaller the value compared to 1 is, so it's say 0.99, that's going to have a lower endurance than 1 which has factor of 1. So we have a choice here which one to use. If you use 0.59, what that will do is it will reduce the endurance strength and give you a smaller factor of safety. And so you can either be conservative or you can be less conservative. So this is really a designer's choice. I'll just stick to the way the book did it, which is Kc equals 1. But in such, if there's an ambiguity, you can choose either of them. This will make you a very conservative designer. If you use this one, you'll be less conservative. So let's use, let me just put this down first. We can use either Kc equals 0.59, will make the design more conservative, as it will lower SE. Okay, let's choose Kc equals 1, which is the one for axial load, and then just move on. Okay, next is Kd. Kd is the temperature factor. And in the absence of anything about temperature in the problem, we're going to assume that this device is going to be working in room temperature, which means that Kd is 1. K is the reliability factor. All you need to do is know the reliability. In this case, the reliability is 99%. So you go to the table and pull out the value for Ke based on 99% reliability. Okay, so we have everything we need. We just write Se as Ka, Kb, Kc, Kd, Ke, Se prime. So Ka is 0.729, or rather rounded it up. Yeah, 73. Kb is 0.87, Kc is 1, Kd is 1, Ke is 0.814. Se prime is 0.5 times SUT, which computed that. That's 52.5. And so Se, finally, we get it as 27.1 kpsi. Okay, so once we have Se, which is the last piece of information we needed to solve this, we've got Se. Now it's just a matter of figuring out the formulas or writing down the formulas for these criteria, and then just subbing in, because everything we need for those things have been determined. So let me just pull this. It'll take me a while to get these formulas. Let me just pull this from my notes. So let's start with Goodman, Gerbers. Okay, let's start with Goodman. Okay, so we need this formula. This is for Goodman. Copy. Okay, so what I need to do is plug in the values. D is 1.1. Okay, SEH is found 27.1. For KFS have been found in the when we found the notch sensitivity and stress concentration. So that is, do I have it here? So that's, sorry, it should be here. So it's 1.37 and 1.58. So KF is 1.58. Okay, MA was found. It is MA is 0. So 1260. TA is 0, so we can just get rid of this term. And then MM is also 0. We can get rid of this. So the square and half here go away, so we are left with only this term plus 1 divided by SUT, which is 105, 3 times KFS.
3. Where's the 4 go?
It's cancelled, right? It's 0. MM is 0. This is 0. And so is this 0.
TA is 0.
TA and MM is 0, yeah. It's right. I made a note here. From here. Here. Should have it in your notes if you took notes. It's there. So 1.42 TM is 1100. So the square and half there get cancelled, and then we are left only with this. Okay, so it's a matter of just computing that value now. It comes out to be.
Wouldn't the first like square root not be there?
Oh, there's another square root here.
KFSTA, yeah. Like because you make that 0, that gets rid of the half there. Should there still be the?
Yeah. So let me see. So the.
No, the previous one. No, the left. Yeah, there, because you make that, because TA equals 0, that means like there's nothing, like you get rid of that square, which means there's nothing to get rid of that. Oh, wait.
I think this should be 2. Right, because there's a 4 KF square. So when you take the half of this square goes away. So you're left with KFMA and then the square root of 4. And then I think you need to get square root of 3 here. Okay, so check the answer. I got 1.52. Yeah. 37. Oh, that's KTS, right? So when you adjust 1.37. Yeah, that's right. You're right. Okay, so I'll quickly put down the equations for the other ones and give you the values. So B is DE Gerber, something like this. 1 divided by N equals 8A divided by pi d cube SE 1 plus 2 B SE divided by 2, sorry, A SUT A is 4 KF MA square plus 3 KFS TA square. P is 4 KF square plus 3 KFS TM square. Okay, which is again copied from the previous section, the notes 1.73. C is DE Soderberg. So in the interest of time, let me put the formula later on, which I'll essentially copy from my notes and put it here. But the answer I get, I'll fill this up. I'll fill the formula later on, is 1.74. And then the last one is ASME elliptic. What is the E represented? TE ASME elliptic. Okay, that one comes out to be 1.74. And then the last one, which is not fatigue, it's the yield, factor of safety for yield. For yield. Okay, for that, what I need to do is I need to find the one Mrs. stress, sigma prime, it's 16 pi d cube times 4 kf ma plus Okay, this part is squared. And then 3 KFS TA plus TM. This part is squared. And then this bracket ends here. Okay, so again, everything here is known, including D, comes out to be 18.21 kpsi. And then if you want to find the factor of safety in yield, it's simply the yield strength divided by the one Mrs. strength. So that's 82 divided by 18.21, and N is 4.5. Okay. Yeah, so this is one of the questions where it's all plug and chug, but once you found the critical things, you need to solve for. Okay, the last question, and that will pretty much end everything we need to cover, and then I'll do the review next class onwards. So this is the last question, and this is, I couldn't find a good drawing for this, so I hand drew this. What I'm missing here is there's a force in the upward direction, 2000 lb. Okay, for the shaft shown below, the mating gears not shown. By mating gears means so these are gears, and then there's another gear mating with that gear. Drive the gears B and D. So this is B, and this is D. Through forces in the vertical direction. So they're meshing with each other, right? And the point of attachment is such that the mating gear mates with B and transmits a force of 2,000 pounds in the upward direction. That's when you essentially remove that one and show the effect of it with a force. And there's a 6,000 lb force in the downward direction. Let's move this down. Okay. It might be better if I move this. Assume that SUT is 100 kpsi, SY is 80 kpsi, and SC, which is the adjusted endurance strength, is 24 kpsi. Compute the factor of safety assuming static yield, using distortion energy. That's the formula which I just wrote down. It's for part E, right, in the previous problem. Okay. And then factor of safety assuming fatigue fill and D ASME elliptic criterion. The thing about this problem is that the actual plugs in Chuck is kind of simple because all you need is, well, you need these factors. You need the, if there is a stress concentration, you need the corresponding KFs, and the diameter is known. So that's not the hard part. The hard part here is to figure out what actually is the moment and torques acting on the machine element. Now, what I did was I drew a perspective 3D view on top. I also drew a side view below, which shows the essential diameters of the various shafts in the lengths. And when we draw the, in this case, the bending moment and shear force diagram.
That 3 or 5 inches, that one on the right, the green.
This one, it's 5 inches. Based on the moment, bending moment, and the shear force diagram, we will be able to pick out which point is actually highly stressed. And once we have that point which is highly stressed, that's the point we'll basically compute these things, factor of safety, right? Because the weakest link is the one which you need to worry about. And the weakest link is the one which has the highest stresses. So the first step here is to figure out the shear force and bending moment diagram, which I'll do first. And then we can proceed with other things. Okay. And piece which I forgot to mention was we need, okay, so we're going to assume that these bearings, which are A and E, are simply supported. So let's draw a free body diagram. So instead of making a new one, I'm just going to put the forces at A and E. So we're assuming that this is simply supported at A and E. So the reaction forces are only going to be vertical, where there's going to be horizontal force also, but that's zero because there's no net horizontal force in any part, right? Okay, so what we do here is we assign a coordinate system. So let's say this is X, that's Y. So you sum the forces in the Y direction. It's VA upward. The 2000 acts upward, so plus 2000. 6000 acts downwards, and then VE acts upwards. So the sum is equal to 0.
6,000, you have 600.
Good catch, 6000. So then VA plus VE is 4000. And then to find the value of VA or VE, we need to take moments about any point. Let's take moments about, let's say, A. So the force VA will not appear. We'll have the 2000 lb force, which acts in the counterclockwise direction, and the moment arm is 2 point. It's actually 1, right? 1 with a negative sign because it's counterclockwise. My bad. Counterclockwise, we'll assume it's positive, so let's just skip the negative sign. Then there's a 6000 force, which is acting this way, so it's clockwise, and the moment arm is 1.5 plus 1 plus 1, so that's 3.5. 6000 times 3.5, and that's, as I said, is clockwise. And then finally, VE has a moment arm of 1.5, 1.5, 1, and 1. So that's, I think, 5 inches, and it acts in the clockwise direction. So 5 for the moment arm and plus for clockwise. counterclockwise. So we have solving for V gives me 3,800. And then you can put this value in this equation to get VA. It's simply 200. 200. The units are LB pound force. Okay, we also can actually figure out the torques. So if you see this, the torque acting at, so the torque, when you find the torque, it's slightly different. It's you need to see the shaft from the either the left or right. So when you see the shaft from, let's say, from the left side, you see that, and since 2000 is on the acting on the right side, you will have a torque of 2000 times the radius of B, right? The torque is force times the distance from the center. And then for this one, it will be, for the 6,000 force, it will be 6,000 times the radius of D, and it will be act in the opposite direction. So the net torque is 2,000 times RB minus 6,000 times RD. And so if you look at the diameters or radii, I think the radii is given. So RB is 9 inches and RD is 3 inches. So if you plug in the values, we have 2,000 into is 9 minus 6,000 into 3. So it's 18,000 minus 18,000, which is 0, which is saying that the system is balanced in terms of torque. The net torque on the system is 0, which also means that, so here the torque is 0 here. It actually increases to 2,000 times RB, and then it stays at 2,000 times RB, which is 18,000 all the way till it reaches here, till here, and then it goes down. And that will be clear when I draw the bending moment diagram, the torque diagram in just a bit. So I'm now going to use this information which I had for the forces and the torque to draw a bending moment diagram, a shear force diagram, and a torque diagram. And that will guide me towards the second part, which is the factor of safety. Okay, so I need to copy that figure again. Okay, let's blow it up a little bit. Okay, so let's draw the shear force diagram first. So they're going to be my axis for shear force. This is V, and this is X. Okay, so on the left side, we have this force here, which is 2,000. On the right side, we have a force, which is 3,800. I think it's 200. My bad, 200, which I found earlier. Okay, so when I draw the shear force diagram, I can go from the left to right or right to left. So to me, so let's just go from the left to right. Won't change the way you start drawing this. So first force is 200 on the left side. Okay, and then the force is constant till I reach this point B, where the force suddenly springs up by 2,000 in upward direction. So I need to go this and then jump up. $2,200. Okay, then it stays constant till the next point, 6,000, where it has to dip by 6,000. So I need to do 2,200 minus 6,000. That comes out to be 3,800. So So minus 3,800. And then here on the right side, it goes back to 0 because 3,800 acting upwards. So positive minus 3,800 negative gives me 0. This is what the bending moment diagram looks like. Sorry, the shear force diagram looks like. Yeah. It starts at 200 because of this 200 force. Then ends here. Okay, let's draw the bending moment diagram. So it turns out that for the bending moment diagram, I can use this trick. I don't really need to look at too much at the free body diagram to do this. I only need the shear force diagram. Okay? You could use the free body diagram and find the right moment and do it. That's one way. I've done that in the class before. But here's another way to do it, which is kind of simpler. What you do is you try to find the area under the curve. So this is 1 inch. This part is 1 plus 1.5. So that's, you know what, let me just put 1.1 inch here also. This is up to this point where there is a change in cross section. And I think those points are critical when you compute stresses. So 1 inch, 1.5, and then 1.5. Okay, so draw the bending moment diagram. All I need to do is find the area that I'm going to show next. So the moment is 0 here. And now to find the moment at the next point, okay, all I need to do is find the area under this curve. So that is going to be 200 times 1. That's the area of a rectangle. So 200. Then I need to find this area, which is again the height times the base. So that's 2,200. Then this area, which is 3,300, just 2,200 times 1.5. And then here it's going to be 3,800 times 1.5 with a negative sign. So it's going to be minus 5,700. Okay, with that, all I need to do now is take this 200, which I found. That will be my first point. Let's be here. So 100. Now from here, go to the next point. I need to add 2,200 to this value on the x-axis. It's 200. So 2,400 is going to be my next point. 2,400, which comes from 2,200 plus 200, or 200 plus 2,200. For the next point, I need to take 3,300 and add it to this point here, which is 2,400. That comes out to be 5,700. And that is the sum of 2,400 plus 3,300. And then you need to subtract that 5,700 from 5,700. So it'll go right to 0. So that is my bending moment diagram computed kind of conveniently without actually writing too many equations. Okay, so the last thing I need to do is draw the torque diagram. That's simple. Let me just try to fit it here. The torque diagram will be, as I said, the torque is 0 here. At this point, right when there's a force in the upward direction, there'll be a unbalanced torque. So that'll be 2,000 times RB, which is 9. So that'll be a torque of 18 torque X. So there'll be a torque of 18,000, which comes from 2,000 times R T. And that will remain 18,000 till we reach this point, and then we dip to 0. So this goes up, comes down. Okay, so we'll need that when we write the B criterions, because it depends on the torque and the moment. Okay, so now the critical part, which is we need to identify which of these points are critical for stresses. Okay, and then we do that by, in this case, the most dominant thing here in the design of shafts is number one, the moment, and number two is torque, right? The torque, if you see, it's all constant from this point all the way to this point, as shown by this graph. So torque is out of the question here. All these points, right from here all the way to here, will have the same torque. So we don't really need to factor in the torque as long as we are between this point and this point in our consideration. Okay, the shear force doesn't appear in those equations, so we can skip that. We only need to look at the bending moment equation, or say the bending moment diagram. Okay, the stresses are low here. So again, I need to focus from here to here. So the stresses are low here, become high here, and become maximum here. It seems like the stresses are the maximum over here. So that might be a point to consider for computing the factor of safety. Another important point is actually this point, and that's why I used it, is because what I need to do is essentially look at the factor of safety at C and look at the factor of safety at D and choose the lower of the two values for the factor of safety. That's what it boils down to. The reason why C is important, even though the bending moment is less, is because there could be a, let's say if the stress concentration at C was 3 times the stress concentration, 3 times without a notch. So what it would mean is that the stress here would be 3 times 2,400, make it like 7,000, which would exceed this. So it turns out for this problem, actually, C turns out to be more critical than D. So instead of doing this for C and D and then picking the lower, the lower of the two, I'm just going to go ahead with point C. But behind that is a calculation which I'm not showing. Okay, so let me write all those things down so that when you refer the notes, you're not wondering why I choose C, even though D has a higher stress. So D has a higher M than C. However, because C has, because there is a change in geometry at C, there is a stress concentration due to which stresses are higher at C than at D. Okay, so the alternate is to check or to compute the factor of safety, or compute N at C and D and choose the lower of the two. Okay, but see, here we're going to just go ahead with C because I kind of know the answer ahead of time. So here, know that C is critical. So we continue with C. Okay, so we need to find the 4 stresses, right? Sorry, the 4 torques. One is TM, second is TA, MM, and MA. Okay, so if you look at the torque diagram, which is drawn here on top. The torque is, well, it says the torque is 18,000, okay? But since, this shaft is rotating, right? That's how it's transmitting this 2000 load because of the spur gears the gears are mating with each other. So that torque is, as the shaft spins, this torque 18,000 is going to be constant 18,000. It's not going to fluctuate between 18,000 and some different value, right? Because the purpose of a gear is to transmit uniform forces. Or in other words, if 2000 is the force between the two mating gears, it will be constant throughout. So this T is basically the mean torque and not the alternating torque. So Tm is 18,000 and Ta is 0. Okay, now let's look at mm or Ma. So this is the bending moment diagram. We have stress at C as 2,400, and that torque is the torque at C, right? So what will happen is when the shaft rotates, this M will actually transition from 2,400 positive to 2,400 negative. Because what's going on here is that the moment itself is constant, but the shaft is rotating, and that causes the moment to alternate between 0 and 2,400 to minus 2,400. So this moment is Ma is 2,400. The steady part is 0. This is lbs inch, lbs inch. Okay, so with that, now I need to compute Kf and Kfs. For that, I need Kt and Kts, and then I need Q, right? So it turns out that the geometry I gave you in this problem is the same geometry which was used here. So I need to take the same figures, that I'll use this figure and this figure to find the Kt and Kts. Okay, these values will change because this has different geometry from the question 2 has a different geometry from question 1, but that's how I'll find Kt, Kts. Once we find Kt, Kts, we'll find what the Newberg constant is from the same formulas, except the SUT is different. Then we'll find Qs and then Kfs. Same thing for bending, which is you find square root of A, Newberg constant, Q, and Kf. And once you do that, it's the same procedure, except that here it's slightly simple. You're already given SE, so you really don't do these calculations. And then the final part is to use these equations. So in the interest of time, I don't want to take another class to do this. What I will do is I will finish up this section, that is find these, and then use the criterion and finish the problem. But there's nothing different from the previous problem in terms of that computation. What's different is essentially this part where I had to draw the shear force and bending moment diagram, and it was not readily given to me.